This computer's recording. All right, cool. So let me start the presentation. Yeah, again, I'm gonna kind of speed through this first part so we can get to the actual questions. But generally, big topics of what you need to know. Um, heap sorting machines, know how sift down works, know when he gives you the ordering. Um, I believe I forget exactly what it was called for the project, but how it's like either like less than or equal to or greater than or equal to, know what that means and how that can affect what heap looks like. Um, know how to go from an array to the heap and know how to go from a heap back into the array. Um, what else? Oh yeah, and sorting machines themselves, know the like know the like 4 or 5 parts to them. You have like heap size, the ordering, all that kind of stuff. Um, Entries. Yeah. Know all of that and how methods like change to extraction mode, insert, extract, like know how those actually affect the structure of the sorting machine. BSTs, know what a correct BST is. You probably don't need to worry about runtime, honestly, but know it, it's good. Yeah, but know what a correct BST looks like, um, the whole structure of them, and also how the same thing as the heap, how the ordering that he gives you, let's say, that's the actual structure. Um, so I'm not sure if you guys can hear, but I'm outside, so if there's wind in the background, please leave it up. Trees, main thing you need to know is for the coding question for trees. Um, those are fair game for this. Um, there is they all follow generally the same process. I have one example coding that we can work through. It's pretty quick, but generally beyond knowing how to code with them, because you guys will get the API. Um, you don't need to know too much else about trees, but linked list is probably going to be a big one. Um, Make sure that you can draw the initial representation for anything, including like 0 smart nodes, 1 smart node, 2 smart node, singly linked, doubly linked, know what those mean. Um, yeah, so and be able to draw it at any point. So like I think for one of your guys' labs you did stack on singly linked list. I don't know if it was singly, but um you guys did stack, at least I believe. Um that would be pretty good practice for drawing. Draw like the initial representation when there's nothing in the stack. Draw it after you push a couple things. Draw it after you pop one of those things. I believe I have something like that coming up. But that is very good practice for drawing. Um, for the actual coding, very similar to how you guys did project 6, I believe, was your linked list project. Um, how to actually deal with the references and pointers to the nodes and all of the other random node stuff. And how to actually like insert something into the list with that code, and then take something out and do all sorts of stuff. I also have a coding question practice for that. Um, um, yeah, and also like extra coding practice for the linked list. If you literally, I think I'm sharing the whole screen, but if you go to the OSU API, CSE, um, if you really want to cover all of your bases, you can try to implement literally everything with a linked list. Like you can do normal list, map, natural number, queue, sequence, set, stack. Uh, I'm I'm sure you could probably do tree, but nah, don't remember that. Yeah, like for like stuff you can do with linked list, these three, queue, sequence, set, stack. Um, if you can do like a bunch of this, because all the implementations are very similar. They just have their little quirks. You should be covered if there would be a linked list coding. Um, but that is always good extra practice. I believe I have map on linked list as one of my practice questions that we'll go through, but feel free to take any of the other data structures and do it on linked list. That'll be good practice. Bugs language, syntax trees. Um, just I believe one, know how to take a full bugs language program and then turn that into an abstract syntax tree. I think you guys have a homework on that. I can't remember. But that would always be good practice. Um, and then there is also the possibility of, instead of giving you guys just a straight bugs language program, there could be like a Java using block and no, sorry, using program statement, and you could like add to block a couple times, and then you add a like while and an if and like if else and a call, and then drawing it based off of those calls to program statement. That is also fair game. Um, but and I can probably come up with a quick bugs language program to practice here in a bit. I didn't redo any, but I sure can do that if you guys want to. Program statement. Um, I'm gonna do program first. Um, Program itself, basically just know that it is a container for three things: name, context, and the body. And context is the map with a string and a statement in it. Just memorizing that is going to get you most of the way there on any questions that he could ask about program statement. Well, for the program part specifically. Um, because I believe, yeah, pretty print. That lab is very, very good practice for most of the questions that could be asked. It gives you the like general template for like getting the name out and then getting the context out and doing stuff with all the statements and getting the body out and doing stuff with that statement. That pattern is going to be like the pattern for lots of the program and safety questions. So know that well, and you probably be fine as far as coding goes. Um, there's also drawing the program statements. We can do that some too. But as far as statement goes, know the whole structure of it. How I believe I forget where I have it, but how like an if has a block as a child. Know the empty representation. That could be important that you guys had to deal with for project 7. Um, how an empty statement is a block with no children. It's not completely empty. I say in air quotes as I don't have my camera on. Um, yeah, but it's not completely empty. You would have to look to the correspondence to really find that out. Also, general advice for all of the coding: look at the correspondence. It'll probably save you, because they can throw in some kind of specific-ish details that like might not be exactly what you think. Like how you would go and do the coding question may not be what the correspondence tells you to do. So make sure you read it. Don't lose silly points on stuff like that. Um, oh yeah, and for the actual coding, no, for the actual coding part, very similar to Pretty Print is basically what you need to know for the statement coding. The whole switch case stuff and how you disassemble it, call it on the children, and then reassemble it. That pattern is also going to be essentially what you want to do for all of the statement codings. Yeah, I have a practice coding question for program and statement coming up. I don't know when this part's done, but yeah, context or grammars. Um, I believe I think I closed it out before, but the one homework that you guys had over context free grammars, that's always good practice. I have a little quick one coming up, but know your derivations, know how to draw a derivation tree, and because there could absolutely be something like for the like bool expression, I think was on the homework. It's absolutely valid and fair game to give you a bool expression and ask, is this valid given this context-free grammar? Or like any other thing, like a math expression, a word, something. That is absolutely fair game. So you would have to try to derive it and then see, okay, can I derive it or is this impossible to derive? Um, that's absolutely fair game, and you should be able to do that. Um, the definitions, terminal, non-terminal symbols, also know what those are. A couple multiple choice questions. Not really multiple choice, they're more like select all. Um, there's direct and sequential access. Direct may also be called random access, depending on the vocab that you use, but just know direct and random are the exact same thing. But for the ones that use sequential access, um, direct is you can get to any part of it at any time with no extra cost, essentially. And then sequentially, you have to go to thing one, then to thing two, then to thing three, then so on until you get to the actual thing you want. So mark all that use sequential. Linked lists are sequential. You have to go from node one to node two to node three. Stack, definitely sequential. You have to pop off a bunch if you want to get something in the middle of the stack. You can't just directly go to it. Same exact thing for queue. You have to dequeue a bunch to get to the middle. Arrays and sequence are going to be your direct, because like if you have like a 10 long array, you can just index at 5 or at 6 and just get into it. That's no extra cost. Same for sequence. You can get the thing at 5 or 6. Know also the kind of downsides for each one. For sequential access, it's usually very fast to add more stuff into your list or into your stack, right? That's not like adding an extra thing. So like say your stack is 10 big, adding an 11th thing is no more expensive than adding the millionth thing, right? But for arrays, they're like one size. So once you run out of space, you're kind of screwed, and you just have to make your array bigger, and that means copying everything over, and that is going to get very expensive very quickly, especially once you get up into like 100,000s. But if you have a huge stack and you want something in the middle, it's going to take a long time to get to the middle, right? They just have drops into funds. Know what those are. Oh yeah, valid heaps. So I gave you guys the array form of the heaps. Um, so this is just the standard, oh, the standard heap that you guys know. Smallest goes on top. He could absolutely flip this to be greater than or equal to, where the biggest thing is on top. Pay attention. But as far as valid heaps go, I can go ahead and pull up my iPad. Share screen. Give me just a second to pull up the notes. Here's one for yes. Okay, I'm sharing screen. Give you guys a second to switch over to my iPad screen. But okay, let me get you out of the way. All right, so the very first, I don't know if you guys can actually see the old PowerPoint anymore. Oh, sorry, I completely missed chats. My bad. I'll go back through. And yes, array is direct access. Sorry if I said otherwise. Array is direct access. I'll go back through chats here in a minute. I was not paying attention. But so I don't know if you guys can see my PowerPoint anymore, but I'm just going to draw on my iPad. So the first one was a completely blank heap. That is valid. A heap can be empty, right? So that would just be going to be like a square or null or something, right? It's nothing. That's a completely fine heap. See, the second one is going to be a single thing. That is still a valid heap. One thing is completely fine, right? This next one If we remember, it's gonna be 5, 1, 2. And so if we go ahead and draw this out, right? Let me grab my thing. I just like to index these, right? So 0, 1, 2, right? And then in the actual tree, it goes 0, 1, 2, right? So then from there, just fill in my numbers. So we have 5, 1, 2. And then that is definitely not a valid heap with the ordering that we were given. That was less than or equal to, which means the root should be the smallest thing in the heap or equal to. So yeah, this is definitely not a valid heap given this ordering. The next one, 3. Let's see, that is probably going to be fine. Yep, smallest. Yeah, children are smaller than the root. Gonna be index 1, index 2. We're good here. All right, this one is a little longer. I have 3, 5, 6, 9, 8. So we'll start. I'm gonna index again. Keep everything straight in my head. Then we start drawing the heap. We put a 3. Then first child is 5. Second thing is 6. And then remember it goes 0, 1, 2, 3 over here, right? This is 4, 9, 8. That is also a valid heap, I believe, because this is smaller than both his children. We're good. 5 is smaller than both his children. We're good. Do that. So yeah, this is also a good heap. And then the next array, I'll probably draw a couple of heaps real quick too. After I get through the arrays, just for more practice. But yeah, the next heap in array form is going to be 1, 1, 1, right? So that's going to look like 1, 1, 1, right? That's also fine because I forget if you guys will have to deal with duplicates, but it is definitely allowed. Like in your sorting machine, you can add like a bunch of ones, and that is perfectly valid, right? And it should be able to deal with that. So this is valid, right? The root is less than or equal to the children, so we're fine. Over on, yeah, let me come up with a couple heaps real quick, just for practice. One going the other direction, and also telling if they are correct or not. So let's do 2, 5, 6, 7, 8, 9. Okay. That is a broken heap because we are not allowed to put things over here without having something here first, right? That's our, honestly, I forget what the vocab word is, but you're supposed to fill in from left to right on the bottom row, right? Right. So you have to go top, do, 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 do. And so, yeah, so watch out for that. Because even though all of these numbers are right, like the root is less than or equal to the children, less than or equal to, less than, right? That's fine. This ordering is broken. So watch out for that. I think that is the only case I didn't really cover on the drawings. Yeah, okay. Let's see here. Thank you, Matthew. Let me get back to the PowerPoint real quick. I'll probably end up switching right back to my iPad to draw, but just to get the all right back here. All right. So context-free grammar practice. This was just a quick mock-up that I came up with. Chat. Um, okay, so for ordering, it just has to fill in left to right. I don't feel like getting my iPad back on here, so I'm just gonna open Paint. Um, for the ordering, yeah, that is yeah. So for the greater than, that is possible, right? We have only dealt with less than or equal to, but technically, if he gave you the ordering was greater than or equal to, then the root would be the biggest, right? So then with that ordering, something like this would be fine, specifically because of this ordering here, right? We've never had to deal with that yet because for sorting machine we did less than or equal to, right? But that is something that you should know how it affects the heap, and watch for that on the questions, in case it is switched around from normal. Um, no, the ordering of the trees don't actually matter. I'm sorry, I'll get to the uh rightmost thing here in a second. But no, the actual ordering doesn't matter as long as both are less than, or I'm sorry, as long as both meet this criteria, right? Pay attention to this criteria, you're good, right? So for us, generally, we do less than or equal to. So I'm gonna do that example. Uh, if I have like one as the root and then I have two children, it is perfectly valid for this one to be 2, 3, or 3, 2. That's completely fine. The root is smaller than or equal to the children, so we're fine. That does not matter. But for the actual rightmost, yeah, so for like the missing things as the heap gets bigger, let me go ahead and draw this a little smaller. I'm not going to do numbers. It's just the shape that we're paying attention to here. But so as we fill in, we have to go on the bottom row, left to right. That's how I always remembered it. So this is so like this top row is completely filled in, completely filled in. So we have to start from the leftmost thing and go left to right, right? So we start here, and then the next thing is here. Next thing goes here. Next thing goes here. Row's full, so we can't go any further. Shift back. It's kind of like a typewriter. Go back here, back here, back here. Da, 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 da. You can just never, ever, ever skip something in the middle. So like if you accidentally forgot to put like this thing here, right? Try to do dotted, that doesn't look great. If you accidentally forgot to put something here and just went straight over here, that is now a broken heap. This is, yep. You need to go left to right on the bottom. Okay. So context-free grammars. If anything else pops up, pop in the chat or to say something. But context-free grammars. This is just a quick thing I came up with. Um, this isn't like a perfect example, but it gets the point across. So say you wanted to go to a city inside of the United States, or like Canada or somewhere else that has provinces. I don't have the provinces or states of any other countries memorized, so I'm just gonna do the US. Maybe I could do Canada, but you know. So um so we have like an address, which is basically just some city in a state in a country. Okay. So practice, you can try to derive Seattle, Washington, United States, or any other cities if you want to use this for more practice. But I think this covers most of the stuff that you could see. Um, Remember for city, how it's like letter, curly bracelet letter. That means it is at least one letter followed by 0 or more letters, right? So that's just so we can actually spell the city. Um, Also completely valid here would be the other way to write kind of recursive definitions in context free grammars, I think you guys had a self-check over that was converting the recursive thing to something that looked more like this. That's good practice. Um, but I find this easier to read. So that's what I did. In examples. Uh, let me pull back up my and then if you want to, I would go ahead and maybe copy this down or take a picture on your phone or something so you have access to it. Um, or I might be able to figure out how to share both screens at the same time. But if it kicks my PowerPoint off again, go and take a picture. Broadcast. If anyone still needs it after it goes away, probably, just let me know. I'll pull it back up. Start sharing. Okay. It's an iPad. So the context-free grammar, I'm just looking on my end. So we have an address, which is and I'll try to write it out here for you guys too. Which is a city, comma, a state, / province, comma, a country, right? So we want to prove that Seattle, comma, Washington, comma, I'm just gonna say US for brevity, but we want to prove that this is valid in the grammar, right? So I'm gonna write the rules as I go. But so let's start drawing the derivation tree, right? So we want to prove that this is an address, right? So, okay, it's an address. Let's start there. What makes up an address is going to be the city, state, and country, right? So since has 3 parts, we're going to give it 3 children. 1, 2, 3. I'm gonna give myself plenty of room, fully. So it's made up of a city, a state, and a country, right? Now, what is a city made out of? A city is going to be made out of at least 1 letter, followed by 0 or more letters. That's why I like to read that. Sorry, let me blow my nose real quick. I'll be back in just a second. Okay, a little better. So what is a city made out of? Oh, yes, sorry. If, yeah, I just put the commas in there for separation. That was, this maybe isn't a perfect example, it's just to get the point across. Yeah, if commas were there and the spaces were there, yes, you would need like a comma and a space, a comma and a space, right? Good catch. But I'm going to ignore that because that is a lot of writing right now. But yes, that is something that you may have to pay attention to. So a city is made out of a letter followed by 0 or more letters. So, okay. This would get very tedious doing Seattle, right? But this is a letter followed by 0 or more letters, right? And then you can keep on going down, right? Or sorry. So this is a letter with a letter, right? So Seattle is definitely a fine city, right? Space. If I had an actual empty space in here, I like if I actually cared and that wasn't just for formatting for myself, um, there would probably be a like, how would that be written? Maybe like, yeah, like, yeah, I don't think that's something that you guys will have to deal with, but maybe I would do something like a space is like pretend that that's an actual space, right? So then you would just like in here space. Oh, it's an empty space, and we're done here because there's nothing more to go, right? Um, but yeah. So looks like Seattle is a fine city. It is a letter followed by zero or more letters. We're good. But yeah, and you know, they would absolutely specify if you had to put the commas in the spaces, right? It's not going to be a trick thing, right? Um, for the state, Washington, um, let me write the rule for the states. State is, I believe I had Alabama or Arkansas or dot 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 because I didn't want to write out 50 states. Um, this is basically just a pick list. Choose one that is in the list, and this is just a list of the states. So in our heads, we know that Washington is going to be towards the end. Yes, Washington is in that list. We are good to say that Washington is a valid state, right? And then for country, let me go ahead and write that rule. Albania, Syria. Sorry if I missed one in alphabetical order. Um, I did my best. So in this list, this is just a list of every single country. I didn't want to write out all of them. The US is going to be later in that list. So yes, we are good to say that the United States is in the list of countries. So we are good on that front, right? So we're good, right? And actually over here for city, I'm gonna be a little more specific than I was. Um, because a city is made up of letters, right? Followed by more letters. So I'm not gonna write this completely out. You guys wouldn't have to do this much tedious work, right? Probably. But this would actually be like a letter, 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 right? And then that would end up, I believe, Matthew, if you remember how to do these, I'm a little rusty on this part. But then this letter would be like the S, this letter would be the E, this letter would be the A, right? And those all map to our picked list of letters, which I didn't write down, but it's just the alphabet, right? Letter A or B or C or dot dot dot, right? So all of those are going to map to letters. We're good. But you would probably have to be something and something kind of specific like is going on down here because a city breaks down into letters and letters break down into these like the actual letters. You wouldn't just be able to skip straight from city to this, right? You have to include this intermediate stuff. That was my bad. That was me being lazy. Um, anything? Um, yeah, no, this is the more correct. Do you need? I actually, um, towards the end, I will go look at the self checks and the homeworks. I don't know if you need this. Let me check this corner. I don't know if you need this, Matthew. I don't know if you remember. Um, you don't. Okay, cool. So, okay, just go straight from city to the however many letters are in Seattle, right? It's gonna have like I don't know how many letters are in Seattle, like 8 or something. Yeah, no, state and country, these are definitely correct, right? These are fine. We just picked it from the list. This is like if this was like a bold expression and it was either like true or false, and we just put like T or F. Like these are definitely correct. Um, as far as the letters go, city would probably have like 8 or 9 letter children. I don't know how long Seattle is. And each of those letters would break down into the actual individual letter. Um, so yeah, let me fix this a little bit for later on. Um, for like maybe if we do like a something more similar to the homeworks where I'm not gonna mess it up because I came up with a random grammar. Um, maybe if we do something like full expression, right? I can't remember the rules exactly from the homework, but you have like trues and falses, right? So like it would basically, I mean, so possibilities um are like is let's see, not T or F and G. Like, is this a valid bold expression? Is something that they could ask. Um, and and like if not, prove it. If so, prove it, right? Um, and proving it would be doing the derivation, either the normal derivation or the derivation tree. Um, don't quote me on this, but I feel like derivation trees are probably more common to do for the proofs, but absolutely know how to do the derivations too, who are on the for that. Let's see. Yeah, so for context-free grammars, and I'm just thinking of, I forget what number homework it was, maybe 25, 26, somewhere around there. Um, with the bool expression context-free grammar. Um, if you want practice, I believe there's the bool expression one, there's the math one. Um, yes, the math one. Yes. I believe you guys had a lab doing something with that too, pretty recently. That may also help seeing it in the actual code, but the more important thing to know for context for grammars, is drawing the derivation trees, um, and knowing how to prove this stuff. Okay. Knowing how the code works might help you understand how the trees are drawn, but um, I think this is the more important part. Uh, okay, let me get back to the slides real quick. Maybe I can actually figure out how to share both screens on one so I don't jump back and forth all the time. Yeah, there we go. Okay. Let me give me just a minute before I put up. Multiple shares. Are we still working? Cool. Okay. Yeah, so you can switch back over to my desktop one. Um, I am going to go ahead and move on to drawing some linked lists. Um, so in the lab, I believe you guys had, if someone wants to confirm, singly linked list, or stack on singly linked list, with one smart node or maybe no smart nodes. I can't quite remember. Um, I am going to change that up a little bit. We're going to do doubly linked list, which doesn't make a whole lot of sense for a stack because we only really go one direction, but it's just for practice, right? Um, but we're going to do doubly linked list with two smart nodes. Um, um, format. We haven't seen the actual midterm. We're just going off of what we know. Um, but it is liable to be a very solid chunk of coding. Um, and because multiple choice are absolutely free game. Um, yes, I'll post the slides. I'll post all the text files for all the code too. Um, but format, I can't make you any guarantees since I haven't seen the actual exam. Um, but yeah, I would expect something. Yeah, similar to midterm one. Mostly free response, drawing, coding, that kind of stuff. If I remember from last year, it was more like your guys' midterm one. I think that's more of his style. Um, but yeah. What was the last part? Um, oh, as far as coding questions can go, literally anything from the labs and the project and anything um similar to those is fair game for the coding questions. I'll have a couple examples after we're done drawing this that we'll go through. That you could absolutely see, or stuff similar to. Um, and I would, yes, quiz questions, and study your guys' quiz 3, for sure. That'll definitely be good practice. I don't know if quiz 2 has stuff for this midterm on there. I don't know if I was around for quiz 2. Um, but yeah, the quiz questions are also very fair game and good practice. Um, Also, after we get done going through the coding questions, I would like if you want even more practice, um, come up with other very similar things. Like there is like for linked list, go and just try to implement some of the stuff from the API on linked list, right? That's good practice. Program and statement, um, stuff similar to pretty print and that and like we'll get them when we get there, but uh yeah, I will come back to that thought. All right, but drawing linked list. Okay. So this slide, for the internal representation, um of a stack on doubly linked list with 2 smart nodes, right? So to start that off, I'm going to actually I'm not going to turn my iPad sideways, but so to start that off, right? We're going to have this as our very first pointer, right? Our triangle, this. And how I always think of it, this is pointing to the class as a whole, right? And I'll usually draw that with rounded edges to differentiate it from the nodes a little later on, right? And this is going to be fairly standard, I believe, for the linked list with 2 smart nodes. This very well may be different if you only have 1 smart node or 0 smart node. But for 2 smart nodes, you're going to have at very least a pre and a post, right? Pre is going to point to our first smart node, and post is going to point to our last smart node. So we go ahead and draw in those. You would likely be given some code or definitely the correspondence, right? Oh wait, crap, you can't see. Can or I think I'm sharing both of my screens now. From my iPad and my normal. Where am I? Where is other me? Sorry, I have not used Zoom in a long time. Is other me? Is other me sharing my screen? Okay, yeah. Okay, okay. Yeah, so I'll give everyone a minute if they haven't found it yet. But okay, so but both of my screens are on here though. Okay, cool, cool. All right, let me go back here. Okay, drawing. Okay. All right. So make sure I did a quick and nerdy correspondence. But that'll matter more once we start pushing things in. But for now, the initial representation is going to look very similar for all of these, right? So 2 smart nodes. So I'm gonna go ahead and draw my boxes. And I do boxes for nodes and the kind of rounded ones for the class itself. That just helps me keep it straight. But and then in our nodes, you would likely be given the class for a node. Um, sorry, there's a loose dog. Sorry, have it. Okay, never mind. Nope, he's with his owner. Okay, good. Okay, but you would likely be given the code for the node class. Um, but for now, let's remember that a node is going to have, for doubly linked lists specifically, a next, a prev, and some data inside of it, right? So let's go ahead and give next, prev, and then I'm not going to write data, but the little block is data. Remember for singly linked, it's only going to have a next, but we're doing doubly linked here, for more pointer fun. Let me go ahead and give this a next, prev, and data, right? You would no guarantee, but if you're drawing the initial representation, you would there's a solid chance that you would be given the code for create new rep. You should probably write. Yeah, let me stop being. Yeah, data. There we go. It takes like 2 seconds. So yeah, next prev data. This is correct now, right? Length. If you are keeping track of length or size, yes, it is going to go in the first rounded box here. I do that later on in the other coding question. But for now, let's not worry about size. But yes, it would go in the class, right? Let me go ahead and actually label this class, and then these are going to be my nodes, right? Like first smart node, smart. You guys don't have to do the labeling on the test, but it can help keep stuff straight in your head, right? So I'm gonna switch over to blue now for the pointers. But so you would likely be given the code for create new rep, but you're going to have pre. This is a general rule for doubly linked with two smart nodes. Pre from the class points to the first smart node. Post in the class points to the last smart node, or the second, right? And now, what do the smart nodes need to do to each other? Well, for the first smart node, next should probably point to the second smart node at first to keep the list in order, right? And then for the second smart node, prev should probably point to the first smart node, right? But then we're kind of left with some extra stuff in these nodes that we don't need at all. So those are left as unknown or null. I believe the most correct way is to draw them as null. And then for data, that is a literally we do not know and we do not care. Just do a question mark, right? So that is going to be your initial representation. Oh yeah, and like Matthew said, even if you are not asked to actually draw these, please, for the love of God, draw them. It makes your life so much easier. It cuts down on so many little mistakes. Like it can take an extra couple minutes, but please do it. It's so much easier than trying to do this pointer mess in your head. Can we be given? Yeah, that's fair game. Like if you were given like if you had like code push and also draw what happens after you push something, that's completely fair game. Yeah. So then let's go ahead and from here take this initial representation and then push on a couple things to our stack. Also my iPad is on 6%, so I'm going to try to speed through this a little bit before it dies because I don't have a charger with me. I will move over to paint if I run out of time. But so I do not have much room here. Let me flip sideways. Hold on. Oh, there. Okay, that gave me not at all much room. Fine, whatever. Okay, so if we want to go ahead, let me copy paste this real quick. If we want to go ahead and insert a couple things into the stack, right? Let's pay attention to our correspondence. I'm just gonna make it smaller. Let's make sure to pay attention to our correspondence, right? Because please, please read this. It will give you all of the information that you need. It's gonna look way more technical than this. but please, please read this. Okay. It it should tell you exactly what to do when you're inserting, where to insert from, where to take from. It will give you everything. Okay. You just need to know how to read it and decipher it. Okay. Let me go ahead. Actually, not delete that yet. Okay. So let's go ahead and push 5 into our stack, right? So put it in the linked list. We are going, instead of, just to be annoying, right? Instead of putting it at the front of the list, I'm doing everything from the back just to make it a little more complicated and fun. So if we are pushing from the back, right? When we go to draw, stuff is going to move second smart node over, so right? Uh yeah, this is the initial representation for two smart nodes doubly linked. Okay. This should be pretty standard across two smart nodes doubly linked. But yes, this is like after you call create new rep, right? Or like call it like new constructor. This is what the internal representation of the linked list is going to look like. Two smart nodes, the class as a whole, everything's set up nicely for us. Okay. So now let's go ahead and push 5. Okay. Push 5. Okay. So when we do that, we are going to, since the correspondence tells us to, add and remove from the right side. Okay. So from the right side basically means that we are going to go over here, right? And then we're probably going to have to fix some pointers, but let's go ahead and just make our new node down here, right? Let me make it the nice box. Oh, that's too big. All right. So our node, right? We're going to have a next preview and some data, right? Data, didn't give myself room. And now we're actually going to have something in the data right now. Instead of question mark, it's going to be 5, right? So now what do we do with the smart node? Okay, we're actually going to have to put it into the list, right? And we know that it should go around right here, right? Because it goes into the back of the list. So let me go ahead and make this a little smaller so it fits. Okay. So, with these smart nodes, right? So now the first smart node is going to point to the first thing in the list with next. And since it's only one thing, the second smart node is going to point back to the only thing in the list with pre, right? So these already look pretty correct, but now we actually have to change around some stuff. You won't actually have to change around the pointer for post. It's still pointing to the second smart node, but since the structure got a little messed up, uh, I'm just going to pre-drawing that. That wouldn't be in your option code. Okay. But now, as far as actually assigning stuff, you're going to have to make next point here, this pre point over here, right? But then for the node that we're inserting, next should point to the thing after it, which is right now the second smart node. And pre should point to the thing before it, which is the first smart node for now, right? So that's going to be how it looks after you push 5. Okay. But now say we want to push another thing on 10. This is where you actually have to pay a little more attention to the correspondence, right? So let's go ahead and push 10. Okay. So let's go ahead and draw the node. I'll just make this smaller later. But so we have, same as always, it's a node. It's going to have a next, pre, and we're going to have data, right? And the data is going to have 10 because we push 10. So now, paying attention to the correspondence, we add and remove from the back side of the list, right? So that means that we're going to add and remove from here, not from here, right? So let's go ahead and start getting ready with our drawing. So we know that this is going to go roughly here, right? Let me make it even a little smaller. Sorry if it's hard to see, but these drawings get a little funky. So let's see. So next needs to point. Sorry, let me go ahead and just redo these arrows. So next is definitely going to need to point to the next thing in the list. This needs to point to the same list, right? So the same. And then this next should point to the next thing. This previous should point to the previous thing, right? So there is push 10 actually inserted into the list and it drawn out. Okay. Let's see. Chat. All right. So then if we want to pop something off of the list, right? Remember, it is a stack, so we insert and remove from the exact same place. Okay. So let me go ahead and copy this again. All right. And so we said that we remove from the back. So the back is the right side. So we want to remove the node that we literally just put in there. Okay. So that is going to look like basically snagging this along with that, right? And then then the actual pop method would return the data inside of here. So if you're actually coding, you have to worry about that. But since we're just drawing, we don't right now. So ignore all the stuff they got left over here. But that is 10 popped out of the list. Okay. It just goes right back to how it was in here when we push 5, right? Exact same drawings as okay. Okay. I believe I'm done with my iPad. We may need to come back to it, but it'll probably die before we need to. Well, let me go ahead and because I'll just need to use paint if I need to draw more. That's fine. Back to the slideshow slash coding questions now. Crap, sorry. I will send along with the PowerPoint. I will put all of those in the same place. Okay. I'll upload the good notes file and all that. Sorry, my bad. Yeah, but I'll put all that out there. Okay. Okay, so coding. Yeah, sorry, I already left the Zoom call. My bad. My bad. Okay, actual coding questions. Let me go ahead and get out of this presentation. And hop over to Notepad++. Okay, let's see. I believe actually while we're on the topic of linked list, let's go ahead and do this. It will likely take a minute. But yeah, because we just drew all the linked list, so let me actually break back out paint. So give me just a minute to mock this up again, right? Just know this is probably not going to be the most correct because I'm probably going to be a little lazy because paint is paint. Free. Also, sorry if any of this is hard to read, but paint is paint. All right, so same thing, doubly linked with 2 smart nodes, right? All right, and then so the top thing is going to be next, right? I'm just going to write N, P, and D. Okay, save myself a little bit of writing. The data is question marks. It's create points here. And these are both nulls. Okay. So initial representation, right? There is the code for initial representation. Note we are doing map on linked list here, not stack, right? And I should have probably added this. I can't spell correspondence, but correspondence maybe. Sure. Uh, insert into the beginning of the list. Yep. Okay. So let me grab paint. So now instead of from the back, like I did just to be annoying, oh sorry, pre-a point here, post a point back here, right? Now we're all set up. Okay. So instead of like last time, we're just like normal, inserting into the front, life is good again. Okay. So this is the code for the initial representation, right? Should if I can pull up, hey, there we go. So this was first, right? Because first smart node. This thing is second, because second smart node. And then you make first dot next equals second, right? So this, so first, let me write F and S. F. First, next points to second, the node as a whole. And seconds pre points to first, the node as a whole. Okay. And then also here, like earlier when someone asked about size, we are keeping track of size here. Yeah. Uh, yeah, if yeah, the ODI test. Yeah, sure. If there's the abstract tree from that, we can definitely try to go over it. Okay. Um, I don't know how you want to send it or paste the question. Yeah, I mean, if you can send it straight in the Zoom chat, I can try to go over it later. Yeah, cool. Yeah, I will come back to that. Okay. But yes, we can. Yeah, that was the really annoying one if I remember right. Yeah. Okay. Yeah, we'll go over it. Okay. All right. So also here we are also keeping track of size, right? We didn't have to worry about it earlier in the other drawings, but we are here. Okay. So if we want to add something into our linked list, okay, play. I drag you. Okay, you know what? Perfect. Okay, we are inserting into the front, right? So if we want to add something, it's going to go right here. And then it's a little small. I can't really draw it too well. But since we are doing a map, inside of the data, the thing that we are inserting, if over here on Notepad, we are inserting a map.pair, right? So in each data would be a pair. Yeah. So I'm just going to write like little brackets because I can't write inside there, but know that this is a pair. Okay. And then make the pointers go right. You're going to have to go there. You're going to have to go there. Okay. So as far as actual coding goes, all of this is going to look pretty similar for all of the implementations of anything that you can do. As far as the two smart nodes, doubly linked, right? It like if you do like set, map, queue, whatever, they're all gonna look pretty similar. But just know the little quirks. Okay. So when we actually want to insert something, right? If we go through the steps of what I just did, first we need to actually make a new node. Where I'll figure out how to post the meeting. I'll make an announcement once everything's up. It's probably going to be later on today. I'll try to do it pretty soon after, but I need to drive home and all that, so it'll be up decently soon. Okay. Yeah, but so the actual micro steps for what I did here, I made a new node. So let's make a new node, right? So it's going to be a type node, and I have the actual class here now, right? Here's the class node. It has a map.pair as data, and then 2 pointers, right? A node and a node, right? Right down here to add, I'm going to call it new node equals new node for the constructor, right? So there's our new blank node made, right? And then let's go ahead and put the data in there before we forget, right? Data equals what got passed in, x. Okay. So there is essentially, before we change around all of the pointers, this is just a blank node with the data now inside of it, right? These don't point anywhere yet, okay? So now I like my next step to be making making these guys point to the correct places, okay? Because if you do the step first, or sorry, if you do the other step first, where you change around where these guys point, you can sometimes accidentally mess stuff up and lose access to stuff that you needed access to. Because pointers are fun. But yeah, I always like to start with these two first. It is, I believe, the safer option. So I would suggest you guys do it too. But so I'm just gonna say fix new node pointers. Okay. So where does all right, so actually even for more this demonstration, let me go ahead and pretend like we are inserting a second thing because sometimes the drawings can be a little misleading if you only have one thing inside. Okay. Not that you shouldn't use the drawings. Again, absolutely please use the drawings. But sometimes they may lead you a little in the wrong direction if you don't have enough in the list already, right? So to make sure that I'm doing this right, I'm going to pretend that I'm inserting a second thing, right? So here's the new node, right? New, no, holy crap, that's horrible. Okay, so it's gonna have a next, prev, and nope, don't have that today. And data, right? Oh, correspondence for this one, we're inserting into the beginning. Okay. I switched it up on you. The data again, right? So we just put the data in, so it's gonna be this thing, right? Blah, blah, blah. And so remember also at this point, we have not changed around these pointers at all yet, right? Because all we have done in our code is make the new node and put the data in. So as far as the list itself is concerned, this thing is still pointing over here, and this thing is still pointing over here. Okay. But we will need to fix that before we are done here. Okay. So first step, since I believe it is the easiest thing, also this should still be going over to the second smart node. Okay. I believe the first easiest step is to make these point to the correct places. Okay. So next should point over here, and prev should point over here. How do we do that? Well, I think or actually no. Let's start with next. Okay. So if we paint, please, there we go. Okay. So new node dot next gets us this triangle, right? And we can change where it points by doing that. So let's start by typing that out. Then from there, where does this need to point? Because remember, we didn't have this arrow, right? So where does this need to point? Well, it needs to point to this node, right? And the only easy way, the only reliable way that we have access to that is through this dot pre dot next, right? So that takes us to here, and then dot pre gets us this thing, and then we go over here, and then when we do dot, we grab a hold of this arrow basically, right? I don't have a lasso, but we grab a hold of this thing, right? And so when we say new node dot next equals this dot pre dot next, we make this point to where this points. Okay. It can get a little confusing, but this dot pre dot next. Okay. And now if you want to fix the prev, right? how do we get to that? That is going to be new node.prev. And then we need it to point to the first smart node, right? So that's just going to be this dot pre, right? Because this pointer needs to point to the same place as this. So it's just going to equal this dot pre. Okay. Now to fix other pointers. We will, so now the first smart node needs to point to new node, right? So we can do that by doing this dot pre dot next, right? Equals new node. Because this dot pre dot next, right? This red arrow needs to switch over. Sorry if it gets a little messy. I'm gonna draw in blue now. This needs to point here, right? And this needs to point here, right? So now this one was easier to get to. The next one is going to be a little messy to get to, but we can get to this other node here, right? We already set new node dot next to point here, right? So that gives us easy access to the node that is just in front of it. Okay. So let's start by doing that. New node dot next. But then we don't want the node itself. We want to change where its previous points to, right? So it's going to be new node dot next dot prev. Okay. That gets us a hold of this. Okay. And then we want this pointer to point to new node. So it equals new node. Okay. And that's add done, right? Besides accounting for size, right? That's 1 plus. Because we have to keep track of size here. Okay. But that is the code for add done. I have the keys and all of this out there. I'll post all that once we're done. But and then there's also the statement in program. I have a pretty decent skeleton laid out, I think already. We can go through that. But hold on, let me pull it up. Yeah, there it is. It's a little messy, sorry. But I do want to go look at that test question real quick. Actually, I may need to use my iPad to do that. So I may solve that later today. Because my iPad's dead now, and doing that in Paint would be absolutely horrendous. So I will probably solve that later. And post the solution when I get all of this out there. Okay. Yeah, and yeah, that is honestly, it can help keep stuff a little straighter in your head. I honestly like doing a little more messy for more pointer practice. But yes, that is probably a better way, right? Yeah, if you want to do that, you can just do like node q equals this dot pre, right? And then everywhere that I said this dot pre, you just copy paste in q, right? Same code, and actually equals q. I think I got all the dot pre's. Yeah, same exact thing, right? It just makes it shorter. I just like doing the this dot pre for even more pointer practice, but yes, I may do this on the test because it can help keep stuff a little more straight. I forget what site that's through. They changed it up. I don't know when. I forget the link. Matthew, I think knows. I mean, if he's still here. There you go. Yeah, but that is extra study materials. They'll have the occasional old tests for you to use, not for every single class, but it's good. Use it, right? It's there for you. Not necessarily for your professor, but just a practice test sometimes. But yes, it is a very good resource. Please use it. Yeah, so I'm gonna leave the rest of these for the linked list because they take a while to go through and draw. I'm gonna go ahead and move on to the statement program real quick. Because I would definitely expect some statement program, because you guys had a whole project on it or two. I forget how many at this point, but and Bugs language and all that. It's a big topic. Okay. So all of these are going to follow the same process. Okay. Um, like same as pretty print. I literally went to the pretty print lab and copy pasted the switch statement, okay, and just deleted all the printed stuff. This is a setup. I don't know if you would get all of the setup. You may have to type the or write this stuff out yourself. I would expect you to have to write this out yourself, so know how to do that. But just for speed, so we can get through this, I just copy pasted it. Okay, but know how to remove, how to add. Always do new instance. Okay, so over here for program because I like starting with that. Remember that it is like all it is a container for three things. Okay, like hammer that home. It is just the three things, and and when we're doing like so the actual program here is we get passed in a string, right? And every instruction that matches this string, we count plus plus. Okay, so like if we want to find the number of infects in our program, we'll pass in infect and then count the number of infects. If we want to find turn left, we you know, we'll pass in turn left. So into every single statement inside of the program, okay. Yeah. So let's start by no, this isn't the ODI question. I will try to work through that later today. I'll need my iPad. Let me go ahead and download that actually, so I don't forget. Okay. Um, I'll work that and I'll work through that later for you guys and post it with all this stuff. But yeah. My email, my last name .132. Um, I don't know if it's on Carmen or not, but let me. There. Um, so okay, as far as count instruction goes, so if we wanted to get the name out, we could, but we don't really care about name here. Like we're not gonna need it. We're just counting the number of the instructions. And name is just a random string. We don't care about it here. We don't need it, right? Oh, my bad. Um, never mind, never mind. Okay, but now what we actually care about here is going to be the context and the body, because we need to call count instruction on every single statement inside of the program, right? That is our main job in this one, right? So we need to get a new context, right? So context. I'm just going to call it C, sure, equals this dot new context. Good. Get the new context, and then we actually want to get it out of the program, so we're gonna have to swap, right? And then I just like this for good practice. We swapped it once, so we know we're gonna have to swap it again after we're done with it. So I don't forget about it. I go ahead and write that in just to really make sure I don't forget about it. Okay. Now probably the easier way to do this is with a for each loop and just loop through the entire map, right? Yeah, that was wrong. My bad. Yep. Thank you. Yeah, sorry. It is a map of string and statements, right? So we need to get every single value out of this map and call count instruction on it, right? So when we're actually and so we actually need to return the count to. So let's go ahead and just make our count, right? Equals 0. And then we know we're gonna need to return it. So return count. Okay. And then actually let me go ahead and finish formatting this. Body stuff goes here. Context stuff goes here. Okay. You can really just split it into the three parts every single time and deal with it that way. Okay. So a for each loop is probably going to be the easiest, most intuitive way to do this. I'm going to show you guys the other way, which uses 2, and a while loop. I don't know if he would specifically ask you to do this, but it is something that you should know how to do if you use for each in the lab and for all the other program stuff. So I just want to show you guys how to do it. Okay. So for this, the whole idea with the while loop, we're going to remove from C, right? Because we're actually swapping everything into C. We're going to remove from C, add into C copy. And then at the very end, swap from C copy, right? Because everything from C will now be in C copy. Okay. It hopefully makes more sense after I do this loop. Okay. So we need to loop while there's still stuff in C. So while C dot size is greater than 0, right? So while it still has something in it, we need to do something, right? And then we want to get the so let's go ahead and get a pair out. Okay. I feel like that's first order of business. Okay. So we're gonna get a map.pair, right? I'm just gonna name it pair equals C dot remove any, right? Because we don't care which one it is, we just want to get something out. Okay. And now from this pair, because we need to get at every single statement inside of the program, I believe it's pair dot value. You may very well have to do all of the code that I'm doing here. Okay. It may not be necessarily counting the number of some instruction, but this is probably good practice for something that you can expect to see, like the idea behind it anyway. All this is testing is that you know how to get stuff out of the program, and then that you know how to do the statement stuff. Okay. The actual like thing you're doing doesn't matter that much. It's really just testing. Okay, can you get every can you get every statement? Oh, kernel. Yeah, I can't. That's definitely fair game. Um, you could absolutely have to do that. This is I don't say more likely because you guys did a whole project on it. He can absolutely just give you a coding question off the project, say do it. He's done that before. But yeah, something like this is also good practice. This is more similar to pretty print, right? Yes, no both, no both. I can't give you an answer one way or the other because I honestly don't know. So, I can't remember if it's parentheses or not. I'm just gonna do parentheses for the value, right? So let's get the value out of the pair, right? And so this is now a statement, right? And now we're pretending that statements have this count instruction, instance method, right? So since this is a statement, we can do dot count instruction, right? And then that's going to return us the count for each thing in the context, right? So this is adding up the amount of instructions in every single thing, right? But now, since we removed from C and we're doing it with a while loop, which is just a little more complicated, we're gonna have to add it back into C copy. Add, and then we need to add the pair, right? So that just gets it back into C copy so we don't lose any data at the end, right? And then at this point, so once C is empty, we know that everything is going to be in C copy, and we are okay to just swap it right back in because everything will be there. Okay. So basically know this pattern. For like if it asks you to like go through a program and do something to like the instructions or like I think you guys I forget exactly what the question was, but it might have been like simplify if else. I feel like was a thing. Um Something like that. Absolutely know how to do that. Practice pretty print, right? Come up with stuff similar to this is always good practice. But everything is going to follow this basic structure. Okay. But whether you use a while or for each, it's swap stuff, loop and do everything, swap it back. Okay. Yeah. And then for the body, exact same idea as the context, but there's only one thing, right? So, and it's just a statement this time, right? There's no string statement. the statement body equals this dot new bodies. And then we need to count plus equals. This is basically going to be the exact same as what was in the loop up there. Okay. Oh, and also this should have had parentheses on it. And then, sorry, I forgot to swap. Please do not forget to swap. Okay. Swap body. Okay. What do we do? Okay. So that I made count instruction and instance method on purpose. If I did, I believe, static, right? That turns it into not an instance method anymore. So also pay attention to whether it's static or instance. If I change this to static, it would be exactly like you did in the chat. Okay. But since like imagine that this is like not the kernel method, but like in like another implementation of math, that's just an extra method that is given, right? So it is actually yes, yeah, no, yeah, pay attention to whether static or instance. I probably should have mentioned that, but yeah, no, this is specifically instance. Okay, so that's why we do the dot. Do you mean like actually passing it, like if it was static, passing it a like statement S? Is that what you mean? Um, both equally likely. So sorry, I can't really give you a straight answer. Um, know the difference and know how to deal with both of them. Okay. If it's static, you're gonna have to pass the statement like as like actually in the parameter list like this, right? But when it's instance, it's just gonna be dot the you use two dot font, right? Like dot value, dot new context, dot new instance. Okay. Just like all this. All right, but as far as body stuff goes, we new body, swap body, we do the thing, whatever that thing may be. Um, content stuff, body stuff. Like, wait, like, what do you mean expect like the code, the context, and body stuff? Sorry, I'm gonna keep typing real quick. To keep us chugging. Yeah, yeah. All of this stuff above here. Yeah, so this is the context section. This is the body section. And then we didn't need name, but if there was a need, okay, sorry. If there was a need for name, like in pretty print, you would deal with that up here. Okay. I like to section it out and make sure I do everything. So yeah, this is the basic format for anything where you need to go through a whole program and do something to all of the statements. Okay. Swap and or well, as far as context goes, swap, loop, do the thing, swap it back. For body, swap, do the thing, swap it back. Okay. That is going to be pretty constant. Down in count instruction, I'm only going to, or well, most of these lines are going to be pretty similar because I already did a lot of the setup for myself. But you would be on the hook for knowing that in block, you loop, and remove from block, add to block, right? In if else, you have two statements, and you have to disassemble and then reassemble, right? You're on the hook for all this code. Okay. Just for speed, I just put it here. So all of these codes is basically going to be the same thing, right? So I'm going to do for practice block, while, and call. Feel free to do if and if else, but they are, the same thing, basically. So for block, since we are already looping through the entire length of the children and removing all of the children, we need to call, and since blocks have a lot and can have lots of statements as children, right? we need to call count instruction on all of the block's children, right? Because since we're looking at the actual instructions, most of the actual work is going to come from down here in the call case. Okay. So we don't have to worry about that in the block. But oh, also here, I forgot it. We should also have a count equals 0 here and a return count at the very end. Okay. So here for block, since we are already getting every single child out of the block, right? And child is a statement, so we are completely free to, just like in the top, count plus equals child dot count instruction. Okay. And then I can and also you could on the test, you can't copy paste, but this is the one line that is going to do all of your work. Basically, this is a recursive call. You're all good. So I can take this straight down to while, right? And so we disassembled it, right, into S this time, right? So instead of child, it's just going to be S dot count instruction, right? Because we want to count all of the things inside of the whiles block, or inside of the whiles children, right? So same exact thing. Most of the code for these is going to look very similar. Just know that block is looping, and then know that like these three cases. Oh, the switch case. He may very well ask you to do all of them. I don't know, right? I assume he would do something kind of similar to what I'm doing to make sure you know all the different cases, like a block and an if and the call, because the if else, and while are all basically the same thing. Like I can literally just copy paste this one line, and if also works, right? And then if else, you just have to do both of the statements. Um, yeah, these three are the same thing, right? So maybe to just cut off on time, maybe he'd only do a few of these, but there's still a lot of writing to be done. Okay. Don't think there isn't. All right, so call is where the actual block, especially know that this is looping. Okay. Um like because like this thing is special. Call is usually special because that's usually where the actual work of the method happens. And then if else, and while are all basically the same thing. Okay. So down in call, we actually have to do the counting here, right? We don't just get to do count plus equals anymore with recursion, because here we actually have to check. So we already disassembled and got our string, right? String S. So all we have to do here is if S dot equals, what did we get passed in? I forget what I named it. Fine, right? So if so if the instruction matched what we want to be counting, count plus plus. That's all the work, right? That is all the work that this thing needs to do. Now, I don't know exactly what you guys will be getting, but something like simplify if else is very good practice, right? Um, yeah, coming up with other stuff similar to this would also probably be good practice. Um, but just know that all of these follow a very, very, very similar pattern. Um, once you can get that down, you should be all right. Okay. Again, I have all the keys for all these. I'll post it. What else is there? iPad's dead. Um, there's tree recursion too. If you guys want to do that, I don't know if we need any of that because I believe that was one of the questions on your guys' quiz. You're still on the hook for that too, right? Study that. Um, if anyone wants to do that, we can. Or if there's anything more specific that you guys still want to go over, instead of this, just let me know. Because I'll probably I don't know when I need to call it quits, but if there's anything specific that you guys want to do, let me know and we can do that real quick. Okay? Or let me check if there's any chats on this. Or anything I said to come back to. Yeah, okay. Okay, all right, I'm gonna go ahead and work through this then. As far as the ODI question, I'll work through that later today and post it and make sure to try to get that to you guys. Um, but let me go and chug through this because tree is essentially the same idea as block, right? Same thing where we have to, or well, as all the statements, I guess, because they literally are trees. You guys saw that on the back end, right? Where we have to disassemble, do something, reassemble, right? All this is going to follow the same process. So let's see, check. Okay, so we are going to actually be returning a Boolean here, right? So let me go ahead and make that found equals false, sure. And then make sure we return that at the end. Okay, that's some pretty good setup. So if we want to actually get through the tree, we need to disassemble it, right? So, and it is a tree of ints, right? So the root is going to be an int when we disassemble, right? So int root. If I remember the stuff off the top of my head, tree dot disassemble is that? Let me check the API quick. Tree. Oh, sorry, completely forgot the children. Yep. Glad I checked. All right, so before you actually get to disassembling, you need to make the sequence to hold all the children, right? And make sure you use new sequence of or new what is it? Oh, sorry. Glad you guys have the API. Yeah. New sequence of tree. Okay. Make sure you use this and don't make your own like new sequence of tree of type D, right? Use this method. Okay. So we can do sequence of tree of ints, right? Or actually that should be integer, but it gets the idea across. This isn't completely compilable code, but it gets the point. So let me go ahead and call this children equals tree dot new sequence of tree. Okay. So there's our sequence, and then we disassemble tree and get the root, and then we get our children, right? Into here. And now I feel like the first question we should ask is the root already what we need, right? So we need to check if the tree has a value greater than x, right? So if root is greater than x, then we're done, right? So found equals true. And then that's the very, very base case done, right? But then actually, if the root wasn't what we wanted, then we need to check the rest of the tree, right? So else, and how do we check the rest of the tree? We are going to need to loop through the entire sequence, and call check tree on everything, right? So let me go to the sequence API. Sequence. Okay. So entry. I believe entry is probably going to be the easiest way to get everything. So if we can do so for int I 0, I is less than children dot length I plus plus. Yep. And now this is okay to do, right? The dot length parentheses, the dot length inside of the for loop because we're not removing anything from the sequence. We are just accessing the entry at a position, right? It's not. We're not changing the length of the sequence inside of it. Okay, so this is fine. So we can do check or so we return a boolean. So found equals check tree children dot entry at I, and then we also need to pass an x, right? So this is almost right? I did do the entry correct, right? Entry at 5, yes. Okay. So this is almost right. This is almost working. The only extra thing that needs to be added here is, so imagine that you found it. So this tree has two children, and you found it on the first and didn't on the second, then it would return false because the second tree returned false. You can just add a found or and save yourself some time, right? This is so this is the work of the function done, is what I usually try to think of it as. But then before you're done, you just need to reassemble it, right? So we passed it in, we called it tree. That's probably a bad name, but tree dot assemble. So we put it back how we found it. And then I believe we pass it fruit and children, right? And then that is the whole method done, I believe. Yeah, I think that's disassemble using this tree. Yeah, yeah, that's the whole method done. Oh yeah, the found or okay. So imagine, let's do paint, right? Um, so imagine you have this tree, right? And it's a tree of ints, right? So it has three children, right? And we want to check if this tree has a number greater than 5, right? So we pass in tree and 5 into check tree. Okay. And let's say that this tree has 10, 10, and 2, right? So if we didn't have the found or here, right? If we didn't have this, if we think about how the recursive call would work, right? So we disassemble it, and then we are essentially left. So we check, and the root is not greater than 5, right? So we don't really care about it anymore. So that can kind of just go away into the abyss. Yes, you could also do not found. That's fine. I just like doing this more. But yes, that is actually better as far as runtime and performance goes. Um, yeah, and just personal preference. I just hate having two conditions in my for loops. That's just me being picky. But yes, this would also work completely fine. Okay. Um, all right, yeah, but so at this point, if you forgot either of those checks, you would have this, right? And then so you have the sequence, which I believe is written with parentheses, if I remember right. Comma, comma, right? So it's a sequence of trees, right? So it would end up being called on the first tree, and it's found would equal true, right? On the first tree, because there is a number greater than 5. It would equal true for the second tree, but then it would return false on the very, very last tree. So then we're done looping, and found would return false, right? So to save yourself the grief, you can either do found or. So if it was true once, it'll be true all the time, right? Or you can do the and not found. Both work. Okay. Um, but yeah, same pattern for all the tree methods. It's gonna look something like this, right? Disassemble, do the thing, reassemble. Okay. Uh, sequence. Yeah, in actual drawing. Let me go back in paint. In actual drawing here. Um, so if this was our original tree, disassembling it literally makes root equal to the root, right? So like root equals this, right? And actually it's not the tree, it's just the number inside of it. So just root equals 1, right? And then we get left with all of the children inside of that sequence, right? So the thing, so this first thing is at position 0, position 1, and position 2, right? But yeah, this would be like children equals this, right? So that's how we're actually able to go through all of the children of the tree. And then if this was an even bigger tree, these would have children of their own, right? Blah 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 blah. Um, but yeah, this is just an example that I can draw quick. Yep. It would work the exact same way. It's recursion. But yep. Um, okay. That's yeah, okay. Is there anything specific that I can go over still? Um, that's all the coding. Or well, not all of it, but this would be good practice for you guys to go through yourselves. I will go ahead and delete this out. There's the key too, right? To compare your guys' stuff to. But yeah, if there's nothing specific, I'll make sure to get this all posted, hopefully within an hour or two. I don't know how long it'll take to drive home. Uh, but I should be able to get everything to you guys. Good. Um, yeah, I think that's all. Okay, cool. Yeah, if nobody has anything else, yeah, I'll make sure to get that test question done and posted with all this stuff. I'll make an announcement or it'll just be in the files or something. Um, but yeah, I'll try to let you guys know when I get everything up. Hopefully by 3 at the latest, maybe 4 at the latest. But yeah, cool. All right, well, thank you guys for coming. Okay. Bye bye. Let me get my screen off. Yeah, I can for all the other sections, I can post it in the general Teams chat. Okay. So you might have to ask your creator to get it for you guys. Because I don't have access to any of the other Carmens. But yeah, I'll post it in the Teams chat too. Okay. Mm-hmm. Still recording.